This is Dr. Holt. This short lecture is on momentum and impulse. In this lecture I'm going to work 4 problems, and these problems are very typical what you would see in a physics class dealing with momentum and impulse. The first problem that I'm going to work is a pitcher claims he can throw a .145 kilogram baseball with as much momentum as a 3-gram bullet moving with a speed of 1.5 times 10 to the third meters a second. What must the baseball's speed be if the pitcher's claim is valid, and which has the greater kinetic energy, the ball or the bullet? Alright, I'm just going to draw just a small little picture here, and it's going to be symbolic of what the bullet is going to look like. So we've got a bullet like this. Alright, I'm going to go ahead and draw then a vector just showing what its velocity is going to be, and we'll have the vector going back this way. Go ahead and label everything. Now the mass of the bullet is going to equal to 3 grams. Now we know we need to get the mass back into kilograms, and we'll do that in just a second. We'll go ahead and label the velocity of the bullet, and the velocity is going to be 1.5 times 10 to the third meters a second. Alright, on this one we know that momentum of an object is always going to equal to its mass times its velocity. So we're going to go ahead and calculate what the momentum of the bullet would be. And we'll do our unit conversions while we're doing this. So we'll go ahead and write it as 3 grams, and we'll go ahead and do the conversion. We got grams here, so we'll put grams down here. We'll put kilograms here. We know that 1 kilogram is the same thing as 10 to the third grams. So when we do this conversion, then immediately we know that grams will cancel out. So we know we're good there. All right. So now we're just going to go ahead and multiply it by 1.5 times 10 to the third meters a second. And we'll go ahead and do that calculation. Then the momentum of the bullet is going to equal to, when we do this, it'd be 4.5 kilograms times meters per second, and that's the units for momentum. Alright, so now we got the momentum of the bullet. So now let's go ahead and we're going to figure out what the velocity of the baseball would be. So we can say the mass of the baseball times its velocity of the baseball must equal to 4.5 kilograms times meters per second. Alright, the baseball is given. Now that's already in kilograms, so we can just write that down. 0.145 kilograms times the velocity of the baseball must equal to 4.5 kilograms times meters per second. And all we got to do is take 4.5 divide by 0.145, and we will find out the velocity of the baseball in this case would equal to 31, and I'm just going to go ahead and put the units down, or I'm not going to round here is what I'm trying to say, and I'm going to get 31.03 meters per second. Now that would be the velocity of the baseball. So we were able to do the first question. Now it says which has kinetic energy. We know that kinetic energy is always going to equal to 1/2 times the mass times velocity squared, and really all we have to do now is just calculate what they're going to be. The kinetic energy of the bullet is going to equal to 1/2 times the mass of the bullet in kilograms, and we'll go ahead and write that down. That's 0.003 times its velocity, and we're going to square that, and we run that computation, we would get about 3,375 joules. Alright, so that's what the kinetic energy of the bullet would be. And now we'll just go ahead and do the baseball. We do 1/2. We go ahead and use the mass of the baseball, and then what was that? That was 0.145. We multiply it by its velocity that we found up here, 31.03. We square that, and we get that. We got 69.8 joules. So we notice right here that the bullet has substantially more kinetic energy than the baseball. Okay, in the second problem, I have a 60-kilogram woman. She's going to jump from a burning building and fall 10 meters before making contact with the safety net, which stops her in 0.120 seconds. What's the average force exerted by the net on her? Alright, so let's just draw, I'll just draw like a rough little building. So we got a building here. We'll do what's taking place here. There's the building. There's the ground. Not a very good picture. We'll have a little net here. And then we're going to go ahead and label it. So the distance from here, we'll make this 10. So she's going to fall 10. And we'll just draw a circle representing her right now. And I'll go ahead and copy that down too. Clone that. Alright, so here she is hitting the net. Alright, we'll go ahead and draw vectors representing her velocity here, and we'll represent the velocity here. Alright, let's go ahead and label this. This would be our initial velocity. Now when she jumps initially, now the secret to this, it's not really a secret, but to make it easy, if she's jumping, when her initial velocity when she jumps is going to be 0 when she leaves the top of the building. And now we need to find out what her velocity final is, and what we mean by velocity final is when she just touches the net. Alright, so we go back to our kinematic equations, and we know this equation here, that Vf squared is always going to equal to Vi squared plus 2 times the acceleration times some, we'll call it delta D, some displacement. Alright, since we're doing, since we're going the vertical direction, you're typically just going to make this y. So I'm going to rewrite this equation as Vf squared is equal to Vi squared, and I'm going to minus 2 times the acceleration of gravity, and we're going to use 9.8 times y. So now all I have to do is put in the units. Now since she's falling downward, I'm going to let y be negative here. So that's going to give me Vf squared is equal to, now the initial velocity is going to be 0. And again, the only reason I'm putting the negative on the 2, and you can put the negative in the 9.8, because typically, not typically, but that is what the acceleration is, negative 9.8. And then we're going to put this in as negative 10. We'll go ahead and run that computation, and we will find out that our velocity final is going to equal to plus or minus 14 meters a second. And since we have anything that's going down to be negative, we can say the velocity at the net would equal to negative 14 meters a second. Get better 14 than that. There we go. Okay, so now let's blow up this area here and look and see what's taking place. We'll come over here, we'll draw another circle. We'll make it a little bit larger. And this, we'll draw the net in red. And let's do a straight line too, because we'll make this good. Oh, I don't want a vector. I'll come back. I want an actual line. Let's go back. Let's go back to here. We'll draw in red. We'll just draw this as this, and then we'll slide that down just a little bit. Okay, so that's going to represent the net. Alright, so that's when she touches the net, and then we'll draw the vector here showing her velocity. Again, I usually don't go in this much detail, but I want to make sure everybody understands this. And now we're going to show what's taking place here. So the net's going to stop her. So I'm going to show what the net's going to look like. And then this ball here, we'll go ahead and clone that down. So that's what she's going to stop. What's taking place here now, you have a force pushing back up, because, change it around here, a force pushing back up. Alright, hope I'm not confusing you with all these diagrams. We'll call this our force. Draw that in red. And we'll have this velocity here. This is just a velocity, and that's going to be our minus 14 meters a second. Alright, now what we know from momentum is that the change in momentum, and the change in momentum is always going to equal to the final momentum minus the initial momentum. And we also know that that change in momentum is equal to impulse, or is also equal to force times time, delta t, right? Because impulse is defined as force times delta t. So we have everything we need. We just need to run the numbers. So we can say that our final momentum, when she stops at the bottom of the net, her velocity's gone to 0. So the final momentum when she stops is going to be 0 because she has no velocity. Her initial momentum going down is going to be her mass, which is going to be 60 times negative 14. Let me run that number real quick and see what we get here. 60 times 14, that gives me 840. So her initial momentum is going to be minus 840 kilograms times meters per second. Alright, so we can say that our change in momentum would equal to 0 minus 840, so our delta momentum is going to equal to 840 kilograms times meters per second. Now all we have to do is set that equal to our force times time, and our time is 0.12. And now when we run that, we will find out the force that the net pushes back up on the woman would equal to 7,000 newtons. Okay, let's look at this third problem. The third problem, we have a car that's stopped for a traffic light. When the light turns green, the car accelerates, increasing its speed from 0 to 5.2 meters a second in 0.832 seconds. What is the magnitude of the linear impulse and average force experienced by 70 kilogram passenger in the car during this time? Alright, so again, I'm going to just draw a circle representing the person here. Go ahead and copy that on over here. Again, I like to draw vectors to represent the velocities. Again, my pictures don't quite line up, but I think you understand where I'm coming from. I'll go ahead and label these. This will be my person. It'll be a 70 kilogram. Has a mass. The velocity will equal to 0. So we can make that initial. And then the final here would equal to 5.2. And the mass, again, has not changed, 70 kilograms. So we know that the change in momentum would equal to the initial momentum. Now the initial momentum is going to be 0 because I take 70 times 0. Put that here. I'm going to subtract 70 times 5.20. Okay, we'll go ahead and run that number there. And 70 times 5.2 gives me 364. So I'm going to write that down here. So that's 364. I'll make that negative here. Alright. And again, the only reason it's going to be the negative, and that's going to help you as far as determining what direction the force is going to be, because we know that the change in momentum is equal to impulse, which is equal to force times time. So we put that in as minus 364. And again, the units of that is going to be kilograms times meters per second. We're going to set that equal to our force, and we're going to multiply that by 0.832. So we can say that the force is going to equal to minus 364 divided by 0.832. Go ahead and run that number there. And that gives us 437.5. And you notice that comes up negative. Which makes sense, because if we think about that regarding the vector, acceleration is going to push. Send your acceleration to the right. The force on the person is going to go back the other way. So the person's going to feel a force of 437.5 newtons pushing them back into the seat as they travel from 0 to 5.2 meters a second in 0 to 5.2 meters a second in 0.832 seconds. They're going to feel this force right here. Okay, the fourth problem. In the fourth problem, we have a friend claims that he can hold onto a 12-kilogram child in a 60-mile-an-hour collision that lasts 0.05 seconds as long as he has his seatbelt on. What will be the required force to hold the child? Well, when you have a problem like this, first thing you're going to do, we're going to get this thing problem in newtons, so I need to convert the 60 miles per hour to meters per second. Now we do know that 1 meter per second is also equal to approximately 2.237 miles per hour. So let's go ahead and convert that. We'll take 60 and we'll just say mph. Multiply it by 1 meter per second. We're going to divide that by 2.237 miles. I'll just do mph again. mph. Sorry, it's a little messy there. Our miles per hours will cancel out, and we'll get our units into meters per second. So let me find my calculator. We'll run that real quick. So if we take 60 divided by 2.237, we get approximately 26.82. meters per second. Alright, so let's find out what's taking place here. We know that our initial momentum here would equal to the mass of the child, which is 12 kilograms. Again, always make sure units in kilograms. We're going to multiply that by 26.82, and that will give our initial. So 26.82 times 12 gives me a value of 321.84. Again, my units are made kilograms times meters per second. Since the crash is taking place, I'm going to come to a stop, so PF is equal to 0. So our change in momentum, delta P, would equal to our final momentum, 0 minus 321.84, which will give us a change in momentum of 321.84 kilograms per meters per second. Okay, so that's going to be what our impulse is going to be, and we know that force times time, or force times delta T, is going to always equal to impulse or change in momentum. So we can say force times 0.05 is equal to negative 321.84. We'll run that number, and we're going to get a huge force of 6,436.8. And again, what the negative means here is that the force, if the crash is occurring to the right, then the force would be going back to the left. That's how much force the person would have to pull back, be able to hold back the child to prevent them from flying forward in the car crash. 6,436.8 newtons is approximately equal to about 1,400 pounds. So it would be impossible for someone to generate that much force when holding a child.